Hello, class. In this video, I'm going to talk a little bit about the connection between the graph theory we've done so far and what's called simplicial geometry, which is basically how you understand three and more dimensional surfaces by breaking them down into pieces. Effectively, you break them down into dots and lines and faces, exactly as we have been doing. So I'm going to start today by talking about how the stuff we've done so far works if instead of doing it on a sphere or on the plane, we do it on the torus. And I've alluded to this a little bit, but a torus is just a single hole donut. It's the surface of that, so you can imagine drawing graphs on this, and that's what we're going to do in this video. But before we do that, I want to think about the model we're going to use of the torus, because I do not want to attempt to draw something on this. And so the way I'm going to always draw my torus is as a rectangle, something akin to this. And at first, that might seem to be, well, not a torus. But what I'm going to say is this is a rectangle, except the top edge here is connected to the bottom edge, or a mathematician would be inclined to say the top edge is identified with the bottom edge, and the left edge is identified with the right edge. So if you imagine that you're a little ant walking around on this this rectangle, then you can walk north and north and north. But then when you get up here, you pop up in the same spot on the bottom, and then you walk over here, and then you pop in at the same place over on the right-hand side. Okay. Now, why is that a torus? Well, that's actually something that you can sort of explain with a sheet of paper. So I'm going to identify the top and bottom. All that really means is that I'm going to connect the top and bottom of the sheet of paper like that, which gives me a cylinder like that. But now I've also identified the left and right pieces. So you have to imagine, because paper doesn't bend this way, that I pull this circle over here and connect it to this circle over here. And once I've done that, then I have something that just literally is a donut. So this is an appropriate model as a way to think about tori. Okay. So to start with, I want to think about the thing we talked about last time, which was that K5 is not planar. Okay, which is to say you cannot draw the graph K5 in the plane. But what I want to try and convince you of is that, in fact, you can draw K5 on this torus. So I need to pick where my 5 vertices are going to go, and to try and make this as easy as possible, I'm going to put 3 in the middle like that. I'm going to put 1 up here, which means it's also down here, because, again, the top edge and the bottom edge are the same. So just to highlight that, I'm going to circle this point in blue. So that's 1 point. It just appears in 2 places. And then I'm going to put the other one here. But because of the way this torus works, that's also there, and also there. So all 4 of those corner points are actually the same point again. So I'm going to circle all of those in red to remind us that all of these are the same point. Okay, and now I'm going to try to connect every point here to every point. There are 5, right? There's the 3 in the middle, the blue point, and then the red point. That's 5. I'm going to try and connect all of these in every possible way without crisscrossing any lines. Okay, so to start with, I'm going to take this triangle right here like this. Okay, and so I've now got this point connected to 3 others. It needs to connect to 4. So everything needs to connect also to the red dot. That's basically what's missing presently. Otherwise, I have almost everything here accounted for. So I'll connect this to the red dot in that way, this to the red dot in that way. I'll go ahead and connect this to the red dot just like that. And let's see, then I've got to connect the blue point to the red dot. I guess I'll connect the blue point to the red dot like this. Okay, and so now I should check that every point connects to every other point. So that means every vertex should have degree 4. So that's degree 4. Aha, this one's not degree 4. Where is this one not connected to? This one here is not presently connected. These two are not connected. But there's an easy way to fix that. Namely, I can just roll over the side and then come back over here. Okay, so now I think every vertex has degree 4. I actually didn't use the fact that blue had sort of a shadow down here. But the red degree I should check, because red has 4 different places that it pops up. And so there's 2 vertices coming from red, there's a third, and there's a fourth. Okay, so everything is connected to everything else. And so we have demonstrated now that K5 is not planar, but it is toric, if you want. This is not the standard word for this, but I'll go ahead and just for this lecture call it toric. Okay, now what do I want to unwind from here? From here I want to think about Eulers Theorem again. So I want to think about the number of vertices, edges, and faces that this graph has as it sits in the torus. So let's count those. So the number of vertices is 5, because this is K5. Likewise, the number of edges is 10, because 5 choose 2 is 10. Okay. And the number of faces, I'm going to have to count. So there's 1, 2, 3. Okay, here's a 4th one. And that's going to connect. And so here's where we have to pay real close attention to the connections, because this connects to there, and it connects to there. So there's actually some giant face that does that, and also it spills out over into here like that. Okay, so that is all one face. Oh, and it even spills from here over to here, which is a little weird. But all of that is connected. And then lastly, we have this face, which is the same as that one because they're connected across. Okay, and so that means my total number of faces here is 5. And so we see that in this case, the number of vertices minus the number of edges plus the number of faces is 0. And so that's actually a theorem. It's a version of Eulers' theorem that for a torus, or a toric graph, as we're calling it, we always have the number of vertices minus the number of edges plus the number of faces is 0. Okay, so that gives us our beautiful thing here. Now, note, you really have to use the torus for this to work. I won't be super explicit about exactly how you check that. But in this case, I know I'm definitely using the torus because we proved that this graph cannot possibly be drawn in the plane, so we know we're doing that. Okay, now you might notice, in fact, there's lots of sort of room to throw more things in here. And so, in fact, you can check for yourself that K6 is also toric, and you should not check for yourself, but K7 is also toric. So there is K7 for you. Notice, again, this is making heavy use of the fact that I can wrap around the edges as one would have to. And so there is K7 beautifully displayed for us as this. Okay. Now 7 is as high as you can go. In fact, it'll be on the homework for you to show that you cannot put K8 in a torus. Okay. But there's K7, just so that you can see it. Okay. Another graph we talked about a lot last time in terms of how it worked on a torus was K33. Okay, so this is not planar, but it is toric. Okay, and so how is that going to work? So the way I want to draw this is I want to draw my three things of each flavor, and I'm going to draw them all across the top of the graph. So I'm going to have black dots and white dots, and I want to connect every black dot to every white dot. Okay, and I've got my 3 black dots and my 3 white dots, but I'm going to go ahead and put this black dot over here again. So this black dot and this black dot are the same thing. And this is going to be the top of my rectangle, which means it's also the bottom of the rectangle. So there we go. So that point up there, it's also that point and that point. Okay, and so my way of connecting everything to everything now is that I'm going to say, okay, each dot here across the top, I'm going to connect over to the dot next to it. So each white dot, now if you want to think about it, is connected to 2 of the black dots and just needs to be connected to the third one. So that is to say, this white dot, for example, is connected to that black dot and that black dot, which is the same. Remember, that black dot's the same as that black dot. So the black dot this one needs to go to is this black dot, which is also that black dot. So I'm going to go ahead and connect this white dot to this black dot. Okay, this white dot now is not connected to which black dot? It's not connected to the black dot that's at the corner, so I can go ahead and do that. And now this white dot is not connected to that black dot, which is the same as that black dot, so I'm going to sneak around the sides like that. Okay, and so now every black dot is connected to every white dot is connected to every black dot, as one hoped. Oh, sorry, I connected this white dot. Once I wrap this around here, doing it correctly this time, then every white dot is now connected to every black dot. And we'll ignore the fact that I did it wrong the first time because I edited it out of the video. So now every white dot's connected to every black dot is connected to every white dot. Okay, and so we can again just verify here that the fancy version of Eulers' theorem, the toric Eulers' theorem, works out. So here we've got 6 vertices and 9 edges, because this is K33. And the faces, let's see what our faces are. Okay, so we've got this region all blacked off. Keep in mind, these boundaries here, they also bound the face down here. So this is one face. Likewise, this, continuing with that, that's a second face. And then this over here, this is a third face. And that's it. So 1, 2, 3, 3 faces. 6 minus 9 plus 3 is 0. Okay. Now we can do a good deal better, because we can even actually embed K44 in a torus. So K44 is toric. K44 is definitely not planar, because K44 has a subgraph isomorphic to K33, namely just throw away 1 point from each. So K44 is not planar, but it is toric. And actually, this picture is a lot nicer than this one. Okay. And if you want, actually, you could have gotten this an answer to showing that K33 is toric in the same way that I'm about to do for this. Okay, so here I'm going to go ahead and label my white points. So my white points, I'm going to label them with the letters A, B, and C, because I want to keep track of which ones are the same. So A is going to be my one that's going to live at every corner. Okay. Then B is going to live on the side, on these two sides. C is going to live here on the top and bottom, and D is going to live in the middle. So here is my rectangle. Okay, and so again, these two B's are really the same point, because when I run off this side, I end up over here. These two C's are really the same because of the same reason. And then these 4 A's are all the same because of, again, the same reason. Okay, so I've just labeled these white dots just so that you can keep track of the fact there's really 4 of them, even though it kind of looks like there's 9. Okay, I'm not going to bother doing that with the black dots, because I'm just going to put the 4 black dots here, here, and here. Okay. And then when I go about this, I now actually see there's a very natural way to connect every black dot to every white dot. Namely, I can do that and that. Okay, notice A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. Okay, so beautifully, we have every black dot connected to every white dot. So we have this really highly symmetric, beautiful picture to show you that really K44 is toric. Okay. Just for fun, let's verify that Eulers' theorem happens to work again. So how many vertices are there? Well, there's 8. There are 16 edges. And how many faces are there? Okay, well, here's 1, 2, 3, 4. Okay, and then I've got a diamond here. That's 5. This is also 5, if I want to keep track. Here's 6. This is also 6. Here's 7. This is also 7. And here's 8. This is also 8. Okay, so there are 8 faces. And lo and behold, 8 plus 16 minus 8 is 0. Okay. So that shows us that K44 is toric. Okay. Now, on the homework, I'll go ahead and have you show that K5, 5 now is not toric. Okay. So next up, I want to talk a little bit about soccer balls. And so I have to think about what exactly I mean by a soccer ball. So here is a picture of a somewhat generic soccer ball. But in particular, what properties of this am I interested in? It is a way of covering the sphere. So reminder, this is back to being a sphere. So we're back to the Euler characteristic being 2. That is on the sphere, vertices minus edges plus faces is always 2. And it's composed of two kinds of things. It's composed of pentagons and hexagons. Okay. So I want to think about the number of pentagons and the number of hexagons. So I'll do this over here where you can see it next to the soccer ball. I'll move the soccer ball over here. So we've got P pentagons, and we've got H hexagons. And I want to figure out if there's any special relationship between the number of pentagons and the number of hexagons. Okay. Now, as a possible source of confusion, I want to show you another soccer ball, this one. And I want to point out this is obviously a very different arrangement, but this is also made up of pentagons and hexagons. In fact, the pentagons in this soccer ball are all colored red, and everything else is a hexagon. And there's another regularity here, which is that in both of these ways of covering a sphere in pentagons and hexagons, every vertex has degree 3. And so for me, that's what I'm going to mean by a soccer ball, is that it's made up of pentagons and hexagons. It's a sphere, and every vertex has degree 3. So let me write that down after I put these away. Okay. So what does it mean? We want sphere, pentagons, and hexagons. Every vertex has degree 3. Okay, so I want to figure out if there's any special properties that have to be true for such an arrangement. Okay. And certainly it's not the case that we can uniquely determine the number of pentagons and the number of hexagons, because I just showed you that it's possible to have a variety of arrangements. Okay. Now, you might argue, rightfully, I'll add, that technically showing you either of those pictures doesn't convince you that either of those meets all of these properties, because these are three-dimensional objects and you could only see the front and not the back. And so who knows, maybe at the back there's some cheating and it just was designed to look like it. But you'll just have to believe me, unless you want to look it up, that really there are a variety of these soccer balls. But they have one thing in common, and we're going to figure out what that one thing is by calculating what the number of vertices is, what the number of edges is, and what the number of faces is. Okay. Now, the number of faces, that should be easy, because it should be the number of pentagons plus the number of hexagons. Okay, so then we have to figure out, okay, what's the number of edges? Okay, well, every pentagon has 5 edges. Every hexagon has 6 edges. So that's 5p plus 6h. But remember there, we've counted every edge twice, because we've counted both sides of the edge, if you want, that side and that side. Okay, so this is 5p plus 6h, all divided by 2. Okay. But by a similar argument, in fact, every edge here contributes half an edge to each vertex, which is telling me by the handshaking lemma that if you took the sum across the vertices of the degree of that vertex, you'd get twice the number of edges, which is to say that you would get 5p plus 6h. But remember, we assumed as part of our definition of being a quote-unquote soccer ball that every vertex has degree 3, so this number is just 3 times the number of vertices. Note I have a slight discrepancy in my notation, which is not going to matter, but I've used capital V for the set of vertices, and then I've used capital P to just be the number of pentagons, not the set of pentagons. So that's why there's these absolute values kind of bars over here, because I'm saying I want the number of vertices, the number of edges, but I just defined capital P and capital H to be the number of pentagons and the number of hexagons. So that means that the size of V is 5p over 3 plus 2h. So this is 5p over 3 plus 2h. And I might as well go ahead and simplify this similarly. This is 5p over 2 plus 3h. Okay. And the thing I know is I know that the number of vertices minus the number of edges plus the number of faces has to equal 2. Okay. Remember, we're back to 2 because we're talking about a sphere now. So it's the Eulers Theorem from the previous video that we now have to refer to when we talk about this. And if I look at this, then I plug in my formulas up here. I'll get 5p over 3 plus 2h minus 5p over 2 minus 3h plus p plus h equals 2. And what I want to notice that you might not see right away is that something very beautiful happened here. Namely, I have plus 2h minus 3h plus h. And so the number of hexagons just falls completely out of the equation. Okay. And then I have 5p over 3 minus 5p over 2. So let's go ahead and write everything over here in terms of sixes. So this would be 10p over 6. This would be 15p over 6. And this would be 6p over 6. Okay, and so that gives me p over 6 equals 2. And so that gives me a theorem that for soccer balls that I have defined in this fashion, p is always 12, meaning there are always 12 pentagons. And so if you grab your favorite soccer ball and you count the pentagons, there will always be 12 of them. They're usually the ones that are in black. And if you look at this and you imagine that you took this crazy large soccer ball and you counted the red pentagons, again, only the red things are pentagons, everything else is just a hexagon, you would find there are still 12 of them. And that's very plausible from looking at this picture, although, of course, again, you can only see one side of it, so you have some reason to be skeptical. But believe me, there will still be 12. Okay, so that's all interesting. And so, sort of to wrap up this video, I want to take the same question, but I want to imagine that for whatever reason, we've decided that we want to build a soccer ball that is in the shape of a torus. So let's say, can we make a toric soccer ball? Okay, so let's see. All right, so first of all, we've got to look back at our calculation about the number of vertices, the number of edges, and the number of faces. And we've got to convince ourselves that this data does not care at all that we're on a torus. All of this works exactly the same. Okay. In fact, a mathematician would call this local data. Okay. Meaning that I don't need to be able to see the whole picture to know how many vertices, how many edges, and how many faces there are. Okay. Whereas the statement that the shape of the thing I'm making is a torus, that's a global statement. I can't see just like a bunch of little pictures and get to the fact that it's a torus. Right? And so really the thing that's profound about Eulers' theorem is that it relates something that on the left-hand side of the equality is purely local. Everything about the number of vertices, number of edges, and number of faces, that's all local. And on the other hand, this number 2, in the case of the sphere, 0, in the case of the torus, that number is purely global because it's talking about something related to the number of holes the surface that you're looking at has. Okay. And so if you want to pursue this angle of simplicial geometry far away, what you'll find is that ultimately what the geometers are interested in is leveraging the fact that they can calculate all of this purely local information and relate that back to this global information about this number, which is called the Euler characteristic of the surface that you're looking at. Again, that's just the thing that's 2 for the sphere and 0 for the torus. Okay, so here on the torus, the number of vertices minus the number of edges plus the number of faces is equal to now 0. Remember, I'm using all the same rules as before for what defines a soccer ball. I'm using pentagons and hexagons only. Well, it's now on a torus. That part we have to change. But we're still putting it together in such a way that every vertex has degree 3. And so using those same rules, we get to the same equation. And so we're going to get to 5p over 3 plus 2h minus 5p over 2 minus 3h plus p plus h is 0 by today's Eulers theorem. And so, like before, the h's are going to drop out. And I'm going to get 5p over 3 minus 5p over 2 plus p. I already did that fraction math over here. It's the same thing. So when I put that over 6, I'll get p over 6 equals 0. So p is 0. Okay, and so what is this saying? This is actually saying that toric soccer balls have no pentagons. Okay, so if you dreamed of me showing you a picture of a soccer ball that had these black pentagons and white hexagons like this, but it was in the shape of a torus, well, I can't do that because there aren't any. The only quote-unquote soccer balls you can make on a torus only use hexagons. Now, I want to point out you very definitely can make a soccer ball out of just hexagons on a torus. And the reason for that is that if you picture hexagons, Well, hexagons are one of the very small number of shapes that can tile the plane. So if you imagine this tiling that you've assuredly seen before, I mean, even just in your bathroom or something, you likely have this tiling. Then, because the torus has this model as being just a rectangle, just a flat rectangle where things wrap around, what you can do is you could just draw a rectangle around piece of this infinite tiling that goes on forever and covers all of R2, and draw the rectangle in such a way that the top and bottom connect and the left and right connect, which is not so difficult. And then you will have your torus. In fact, if you want, you could just do it by taking this piece here to that piece there, and then this piece down there, and then this piece down there. You have to imagine that that was really straight above this. And then you could easily see that this now repeats the way it's supposed to, and then you in fact get this combination of 1, 2, 3, 4 hexagons tiling a torus. And at every place in this tiling, I should mention the vertex in fact has degree 3 like it's supposed to. All right, we'll wrap up there for this lecture, and we'll pick up next time talking about a totally different graph theoretic question. Namely, next time we're going to find ourselves talking about when it is possible to visit every edge of a graph. But until then, be well.